This is Lecture 9C for Calculus 2 on Euler's Method. Okay, what we covered so far was separable equations and the use of an integrating factor. Those are our two analytic methods for solving the differential equations for this class. Now we're going to look quickly at a numerical method. It's called Euler's Method. This is used for first-order ordinary differential equations. What you do is you start with some point on the curve, some initial value, x naught, y naught, or t naught, y naught, t of 0, say, and y at 0. You start with some initial point. The differential equation will give you the slope at that point. You use a linear approximation to get to the next point. There, you find the slope again, and you walk to the third point. You just keep doing this. It's just an iterative numerical method. The exact steps are given in the written lecture. They're also given in the textbook. They're sort of cumbersome to follow here on the screen, but here is the result, and I think this is a kiloword for you. Picture being a kiloword. Okay, here is the first point. So you start with some initial value. Let's see, I need a pin here. So I'm going to start here with this initial value right here. X naught, y naught. So this is y0, this is x0. At this point, due to the differential equation, or from the differential equation, you can find the slope of the tangent at this point. You use that slope and you walk along that tangent line to x1. You'll get some new value, which is y1. Okay. Here, you find that the differential equation will give you another slope. This is a little flatter than the first one. You walk along this tangent to x2, and this will give you your y2. You keep doing that. The blue line in this case is the exact function. The red line is the Euler's method, the Euler approximation. Of course, smaller step sizes give you more accuracy, but then you have to worry about round-off error too. So it is a numerical method. It's an iterative method. Actually, it's not that good, and there are other methods built on this that are better. Here's just a quick example. Let's look at Newton's law of cooling. Now, this is a numerical method, so we don't do anything in general. We need specific values. So remember, Newton's law of cooling was minus K times T minus the ambient temperature. Here the ambient temperature is 25, and K has a value of minus 0.5, a half of 0.5. The negative sign was part of the equation. This is a first-order differential equation, so we can use Euler's method. Let's say we want to use Euler's method instead of solving it analytically. So we have to start with the temperature, an initial value of temperature. So we're starting at T equals 0 and let the initial temperature be 100. So the initial point is 0 and 100. Go back to the differential equation and evaluate the first derivative. This is going to be the slope of the tangent line when T is 0. T doesn't count here only because it's an autonomous equation, and the temperature. So I'm putting T of 100 into this equation. I get 0.5 and times the quantity 100 minus 25, which gives me negative 37.5. That's the slope I'm going to walk along. So we started at T equals 0. So that's my first point. At that point, the temperature was 100. So I'm going to move to 0.1. Okay, so 0.1 gives me my step size. So this is T1 minus T naught. Right here, it's a minus sign, times that derivative. It's just a linear approximation, and I get 96.5. So the next point is T1, time 1, and temperature 1, 0.1, 96.25. Then I keep repeating the process. I have to find the derivative at this new point. Then I move to T equals 0.2, and I find a new value of the temperature. I'm just going to mention here a refinement of the Euler's method. They're what called predictor-corrector methods. Sometimes it's called a modified Euler's method. In fact, there's several kinds of predictor-corrector methods. Now, in this scheme, you take your first step using Euler. That's your predictor, right? Then you go back and you know that you're off by a little bit, so you go back and try to modify it. You take, in this case, you take the average of the slopes, both at the old value and at the new value, and that's your corrector. So it actually works a little bit better. These are numerical methods. When you take a course on numerical methods, you'll start studying those kind of predictor correctors. They just